Hello, I'm Adam Field, a sophomore physics student at WPI. Welcome to my presentation on the Event Horizon Telescope. Today we have three topics, the history, operation, and the future of the Event Horizon Telescope. Starting with the history, we have the inception, right? Shep Doeleman, who's associated with the Harvard and Smithsonian Center for Astrophysics, founded this project, right? And he set the clear intentions of taking the first image of the black hole. A couple things motivated this project, right? The increasing capabilities of the radio telescopes at the time, and the very long baseline interferometry technology that was rising. Along with like this image of a worldwide array, right? Where we take telescopes from across the globe and combine data to make a really sharp image with a supercomputer, right? Combining with a supercomputer. With that image, this project was born. So in 2017, the year that they took their first captures, right? They had 8 telescopes and arrays of telescopes in their array. I want to highlight the ALMA because it's the biggest, right? And then also the South Pole Telescope because it's in the South Pole. That kind of highlights that this thing is global, really global. There's even one in the South Pole. Nowadays, I think it was added in 2018, is the Greenland Telescope array, and that's also showing that it's global. Like there's one in Greenland, there's one in the South Pole, then there's other ones across the globe, right? Some historical achievements. They obviously took a picture of the black hole. In 2017, they took the pictures, right, with their whole array. And then in 2019, they released the images. It took 2 years to develop M87's image using their algorithms in the supercomputer. That's on the left here. I'll show it in a later slide, really breaking down the images. And then in 2022, they released this image on the right of Sagittarius A, the supermassive black hole in the center of Sagittarius A. That's also data from the 2017 captures. On the right here, there's some awards that they won after the release of the M87, the famous M87 picture that was everywhere at the time in 2019. So the Breakthrough Award, it's obviously for a breakthrough, right? This Porsche Award here, the second bullet point, is for the algorithm that they used to develop the image. This third bullet point here is a Spanish award for the groundbreaking discovery in imaging of the black hole. I wanted to highlight it and put it up so high because it's a Spanish award. It kind of really shows how global this project is and how international it is. I think it's really cool when science projects or science endeavors go so global like this is. It usually is it's the making for a really amazing discovery when the whole world works together. This Rossi Award is for the imaging of the actual the process of imaging. The Einstein Award is for advancing theory. The direct synopsis of the award is advancing theory like Einstein did. And this is very topical to that, right? Because kind of when these images came out, it kind of confirmed, not that it needed confirming, but it confirmed the general theory of relativity, right? It kind of gave empirical evidence, even though we had observations that were in line with it, right? But this is a much more material proof of the most deep consequences of the theory of general relativity. This NSF Diamond Award is for the groundbreaking discovery, but more than that, it's the social impact and like the cultural impact that this discovery had. Getting right into operation, we're going to look at some images, but we're also going to talk about how this thing works, right? So they're utilizing very long baseline interferometry, which is just taking images, right? But we're using as implied by very long baseline, we're taking images in the radio frequencies to get a sharper image, and then mapping it back onto the visible light to make it into an image, right? So how do they make it into an image? They use the supercomputers at MIT Haystack and Max Planck's Institute for Radio Astronomy. And why are they using two supercomputers? They did this whole thing in the releasing of M87's image back in 2019, where they had 4 teams independently developing it using multiple different supercomputers in order to really confirm the findings that this data has resulted in. They wanted it to be almost like undebatable. The different algorithms used by the different teams developing that image will be discussed in the next slide. So let's get right into looking at the images. This is again the first image of M87. It looks kind of bad on the TV, I will admit, and it probably looks even worse for you guys because it's a camera on the TV. But anyways, if you really want to see it, it looks awesome. I suggest Googling it. M87 images. It'll come up with a few different ones. We'll look at all of them in the slides. So yeah, they use they use algorithms such as clean, chirp, and what I found to be called a regularized maximum likelihood algorithm. The final picture that they released to like the public and got all the attention used what I understand is a combination, or maybe they just liked both of the clean and a regularized maximum likelihood algorithm. I don't know if it was a combination or not, but I know that they used both of those in their final imaging. And then, oh, sorry, I skipped a slide. This is the image that came out in 2020 of the same exact data, right? M87, 2017 data, same captures, same data, but they polarized the light. Now, I'm not going to get into, in this presentation, what polarizing the light means. We all should know what polarizing generally is, but when applying it to imaging a black hole, it gets pretty complicated, and I would much rather just let EHT explain it. At the very end, I shout out their YouTube channel, but they have 3, maybe 4 good YouTube videos explaining exactly what polarizing is. They also explain what polarizing image is in context of the Sagittarius A pictures that we'll look at soon. They do a lot of explaining on the polarizing side, and I think they do it really well. So I highly suggest watching those YouTube videos. But yeah, this polarization really shows these lines, right? I'm sure you guys can see it. And those are actually the magnetic fields around the event horizon. It's really interesting to see that. And once I get into the future section, we'll talk more about the magnetic fields and how EHT is interested in them. This is the image that they released recently in 2023 using the newest algorithm, Primo. I threw this in there just to really highlight the importance of the algorithm they're using in the final product, right? Just like look at the difference between the clarity of this and this. That's the upgrade in just algorithm. This created a much sharper image. If you Google this image, it's awesome. And yeah, again, it's just showcasing the importance of the algorithm. This is the first ever image of the Sagittarius A, it took 5 years to come out, right? This was in the rounds of the 2017 capture, but it came out in 2022. And the reason it took 5 years to develop was because just the Sagittarius A black hole is a lot smaller than the M87 black hole, right? And it's a lot finer of an image, so it took a lot longer to get a quality image out of it. It took a lot of developing their algorithm to get to this point. And then Sagittarius A polarized, again, that looks awesome, right? I highly suggest Googling it because this is not good representation of how cool that image is. Those magnetic fields are really prominent, and again, they're interested in those. But this is Sagittarius A. I think it's really cool that that's at the center of our galaxy, right? And then they also took some much farther away images, right, of Blazer. I'm not going to read out that name. You guys can see it. This was released in 2022. It was in collaboration with the Global Millimeter VBLI Array and the Very Long Baseline Array. You can see here that they took like varying resolution pictures, right? Like zooming in almost. From right to left. Right is the farthest zoomed out, and then left is the farthest zoomed in. And the leftmost one is the picture taken by the Event Horizon Telescope. Again, blazers are awesome. It's awesome that we can take pictures of this stuff now and really get to understand them. All right, getting right into the future. Again, they have future interests of capturing the developmental nature of, like the evolving nature of black holes. They really want to take longer exposure pictures to understand the time evolution of magnetic fields and the hot spots around the event horizon. Along with those future aspirations, they have a branded next-gen EHT telescope. They're almost doubling the amount of antennas in their array. They're also maybe adding space telescopes to really increase the resolution of this image, to increase the effective radius of this virtual observatory, right? And then they also want to develop their back-end technology to get a higher record rate, and so yeah, they want to increase that technology to really get the data recorded faster and accurately, and then they also want to better their transport of their data. This is all really just trying to increase the efficiency of their machine, right? They hope to increase the transport time, because right now what they're doing is they record all this data on hard drives, like physical hard drives, like terabytes and terabytes of data on physical hard drives, and transport it in trucks to MIT's Haywire and the Max Planck supercomputers, and they combine them there with those physical hard drives, right? And that's first of all dangerous. Like, what if those physical hard drives got damaged in transportation? That's a lot of data and a lot of time and a lot of money just gone, right? They also want to eliminate like the time that it takes for that, because that's a lengthy process of transportation. And they hope to do that with lasers. There was this crazy detailed plan. It wasn't really detailed, but it was cool to read about space lasers and transporting data through the laser and through telescopes. Because you can't just transfer it over the internet. It's way too much data. It would be too hard, too slow as well. So yeah, space laser. they're constantly observing new things as well. It's kind of hard to get like exactly what they're gonna observe next. I saw some things about them observing Sagittarius A again back in April of this year. Not sure if that happened or not. But yeah, that's it. Again, shout out to the EHT YouTube channel. Really informative and cool. This is their channel name, EHT Telescope, or it's each telescope, really. And thank you guys for watching. If you guys liked my presentation. This is the cool one. I figured I'd just go back to it.